We will now continue our study of chemical bonding and nomenclature. In this section, we're going to discuss how to properly write formulas for ionic compounds, discuss polyatomic ions, covalent compounds, how they are named and their formulas, as well as Lewis dot structures for atoms and molecules. Let's begin by discussing formula writing for ionic compounds. The method that we're going to use is often referred to as the crisscross method, because that's exactly what we end up doing. We're going to cross our charges, we're going to lose the sign, and the numbers become subscripts. And then we simplify to the lowest whole number ratios as possible. Let's do some examples to make this make sense. Sometimes this is called the swap and drop method, because that's, again, exactly what we're doing. So using our periodic table, we find sodium. It has a +1 charge. Oxygen has a -2 charge. We're going to cross these charges, and we end up getting Na2O1. So notice I got rid of the positive and negative. Okay. The proper way really to write that is just going to be like this, Na2O. We never write the ones. For calcium fluoride, again, periodic table. Calcium is +2, fluorine is -1. So when I cross my charges, I get CaF2. Tin 4 sulfide, Sn is tin, it's telling us it has a +4 charge. Sulfur is -2. When I initially cross these, I get Sn2S4. But that's not as simple as possible, because 2 and 4 can be simplified to a 1 and a 2, so the correct answer would be SnS2. Finally, aluminum nitride, Al +3 and N -3, initially becomes this, Al3N3. But because they are both 3's, it simplifies to just Aln. Please pause the video and try the practice problems. Now please check your answers. I have crossed my charges on everything using my periodic table to help out, or the provided Roman numeral, and then I've simplified when I could. 2 and 2 can become 1 and 1. 2 and 4, 1 and 2. Again, 2 and 2, they're the same, so they go away. And the same thing with these last two examples down here, 3 and 3, and 3 and 3. Okay. Now we're going to move on and talk about things that are polyatomic. Polyatomic ions are defined as groups of atoms that are covalently bonded together with a charge. So they act like they're a single atom or a single element. You can see some examples provided here. There's also a handout that is posted in D2L with additional ones. You do not need to memorize these. When we write their names or their formulas, the same rules apply as before. So we're still crossing our charges, okay, when we're writing their formulas, and we're using their polyatomic ion names instead of changing the ending to IDE. So let's run through these examples. NH4, as you can see, is called ammonium. Okay, and we know that oxygen, because it's not polyatomic, is oxide. Okay. We have copper. We have an S and an O. We know that this is copper. And then SO3, as you can see here, is sulfite. But copper is transitional, and therefore it requires a Roman numeral. So same thing as before, SO3 has a -2 charge, so therefore copper must counter that and be +2. Magnesium acetate. Acetate is not on this example page, that's okay. Is going to be Mg with a +2. Acetate is C2H3O2-1. We're only going to focus on the charge when you cross. So the final answer becomes Mg. And then we're going to put this whole thing in parentheses and put a 2 outside. So the polyatomic ion has to be denoted with a parenthesis so that we know that that 2 goes with the entire ion, not just the oxygen. And finally, iron 2-phosphate. Iron is +2. Phosphate we have over here is -3. Again, I'm going to cross my charges, just the charges, and this is going to become Fe3. Again, PO4 is going to go in parentheses, and that 2 is going to go on the outside. So whenever you have more than one polyatomic, you always have to put it in parentheses. You're going to get a chance to try some of these on the next slide. Okay. Please pause the video, name these over here, and write formulas for these. Please check your answers. You would know that all of these had the polyatomic ion in them because each of them has at least 3 different elements. Then you would just use the polyatomic ion handout as well as your basic knowledge of naming and writing formulas for ionic compounds. So Roman numerals are still sometimes necessary, and then you only have to put the polyatomic in parentheses if you have more than one. Now we're going to kind of switch gears a little bit. We are going to begin our study of covalent compounds in detail. Whoops, too far. Alright, for covalent compounds, are they easier than ionics? Ionic compounds, you have to know their charges to determine their subscripts. You have to add in all your Roman numerals. You have all these polyatomic ions that make things more complex. Covalent compounds, the name tells you how many. And the formula assists with the name because of prefixes. You're going to want to memorize these prefixes as well. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 hexa, 7 hepta, 8 is octa, 9 is nona, and 10 is deca. Most of these relate to pretty common geometric shapes like a hexagon or a triangle, so they should be pretty easy to remember. Let's talk about how to name and write their formulas. The name is always 2 words, no matter what. Okay, it's always going to be the first element, followed by the second element. It is the prefix and the name, and then another prefix and the name. The first element does not change its ending. The second element will change to IDE. Another thing that's never used is mono on the first element. So if the first element in the formula is 1, you don't say mono, like mono carbon dioxide is not a thing. In addition, we try to avoid double vowels. So if I'm going to name CO, it's carbon monoxide. I don't want to write mono and then oxide because that looks weird. So I get rid of that O, and it's just carbon monoxide. Okay. You're going to keep the subscript with the element, so there's no crossing on these. Please pause the video and try the provided practice problems. And now check your answers. You'll notice I did not change the ending on any of the elements that are written first. They stayed the same. But on every second element, I did change the ending to IDE. When I'm writing their formulas as I am here, all you have to do is look at the prefix. Diphosphorus means there are 2 P, and pent oxide means there are 5 O's. So you're not crossing your charges here. Okay. Keep the number with the element that is directly connected to. Now we're going to kind of switch gears a little bit. We're going to move on past naming and formula writing. We're going to do a little review of electrons, and then we're going to talk about dot structures. First question here says, which electrons are involved in bonding? Okay. The electrons that are involved in bonding are our valence electrons, which we briefly discussed back in the periodic table unit. The valence electrons are the outer shell electrons. So valence electrons are the ones that are in the outermost shell. And our core electrons are all the others. In general, our valence electron number is going to equal our group number. So elements in group 6A have 6 valence electrons. We have something called the octet rule that says every atom wants a full valence shell. Okay, oct meaning 8. So most of the time it's 8. They obtain this full shell by either gaining, losing, or sharing electrons. Our focus is going to be on the sharing within this part of the unit. Our noble gases are going to be unreactive. Let's talk about why. Noble gases are group 8A, so they already have 8 outer shell electrons. The one exception to this rule is helium. Helium only has 2 electrons total, so even though it's in group 8, it only has 2 valence electrons. Let's talk about dot diagrams for atoms. Okay. These are very helpful in helping us kind of keep track of our valence electrons, and they help with our molecular shape, which we'll be talking about shortly, as well as the type of ion that something is going to form. When you write out a Lewis dot structure, you're going to write the chemical symbol, so the X here represents that, and then we're going to use dots to represent our electrons. We're going to spread them out, kind of like we did with our electron configurations and Hund's rule. Doesn't matter where you start. You put an electron here, 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 and here, followed by additional electrons as needed. It's never more than 8. So let's do a couple of examples. Nitrogen is in group 5A, so it's going to get 5 valence electrons. So I draw its chemical symbol, and then I start with my dots. 1, 2, 3, 4, 5. Br is in group 7A, so it's going to get 7 valence electrons. Draw my symbol. 1, 2, 3, 4, 5, 6, 7. Okay. Please pause the video and try the provided practice problems. Now check your answers. Sodium's in group 1, so it gets 1. Mg2, so it gets 2, so on and so forth. He is the one exception. Because noble gases do not form bonds, usually, we put both of its electrons together. Let's continue our study. We're going to talk about how molecules are formed from atoms. In covalent bonding, electrons are shared. They want full valence shells most of the time, and they can form multiple bonds. There are some exceptions. H and He only want to be in contact with a total of 2 electrons. Boron is unique because it only wants to be in contact with 6, and S and P are unique because they can have more than 8. S can have up to 12, and P can have up to 10 usually. There are 3 types of covalent bonds: single, double, or triple. A single bond has 2 electrons, a double has 4, and a triple has 6. Single bonds are going to be the longest, so we're going to rank length and strength. Single bonds are the longest, triple bonds are the shortest, and double bonds are in the middle. And then it's the opposite for strength. So single bonds, because there are only 2 electrons, are the weakest, where triple bonds are the strongest. And then here are a couple of examples of dot structures of molecules. F2 is going to be single bonded, O2 ends up being double bonded, and N2 ends up being triple bonded. In our final video on this topic, we will kind of go through the details of how these are drawn.